So let's say we have a convex lens. So when the light enters this lens, it actually refracts or bends at two places, here and here at both surfaces. I'm going to draw it as if it only bends once, but realize that it has to enter and exit in a couple spots, okay? Now there are two focal points because the light can go either direction through the lens, all right? Since this is a convex lens, it converges the light. So it'll do this, and then this, and along the principal axis, what happens? Yes, good job. Straight through. Yep. Well, for this particular picture, we choose the principal axis. Go ahead, Varun.
So, like, when NASA looks at stars,
Yeah.
like, the, like, star position, like, do they need to, like, recalculate where stars are because, like, it's, refracted or whatever?
Yes, we have to make slight adjustments because of actually multiple refractions. You have the refraction of the atmosphere from the vacuum of space, and then and that changes because the density of the atmosphere changes, and then you usually have, if you're on the Earth, multiple lenses that you have to go through. It, for close distances, has a negligible effect, but for distant stars, yes, it does make a difference. All right, so that's how the lens works. This is why Sid could burn a spot on Woody's head, right? It was this type of a lens. So, what kind of image? So you need to kind of keep this general idea in mind when drawing the images.
That's a flat one.
It's a convex lens. Convex converges the light. Okay? All right, so now let's actually draw the ray diagrams. We have two focal points, and I'm going to put an object out here beyond the focal point. Parallel light ray, and it will follow the same rule as we used for the curved mirrors. Will bend through the focal point. Now it goes through this focal point because it's a converging lens. If you think about light coming through, it has two possibilities. It can hit the lens and aim through this back focal point, or it can hit the lens and aim through the opposite side focal point. This is a converging lens. Converging means brings it in toward the principal axis. Okay? If it did this, whee, that would be a diverging lens. So you have to know, in general, that this shape is for converging light. Convex lens converges the light. So, go ahead. Yes, because light can go either way. Now we need to draw a second light ray to create an image. We're going to draw our second light ray through, well, I'm going to draw it in pencil. One of them's going to be right, one's going to be wrong, so don't draw this yet, okay? So we can go, remember we did parallel through the focal point, so the second is to flip that order. So we could head through the focal point, right, and exit parallel, or through this focal point and exit parallel. So which one is correct, light ray 1 or light ray 2?
Light ray 2.
That is right. HC. How come?
Okay.
Okay.
Actually, so from what I'm beginning to understand is that you want your light waves, if you want to make it upright to the up, one past the focal point. Because if you see over here how the two lines are intersecting past the focal point.
Like here versus here?
Yeah, exactly. And then the other thing is that, lost my train of thought, I apologize.
That's okay. Peter?
Parallel lines have to exit through a focal point, and the first one that you drew was a parallel line that hit the focal point.
Yeah, it's even, you guys are, those are brilliant answers. It's simpler than that. No, this one was aiming through a focal point. This one was. Which one is converging, which one is diverging?
Yes, it's the second one.
Right. So, pulling the light in, converging the light. This one, diverging, pulling it away from the principal axis. You will see this light ray in a couple of minutes in what kind of a lens? Right, a diverging lens, that's correct. So it really, this one does follow the rules, but it's for a different type of lens. Got it? This is a really, really common mistake that beginning physics students studying optics make, and that is to draw a light ray that is correct for a different kind of lens. That's really on the G.
If it doesn't go through the focal point, how does it later?
This one right here?
Yeah.
It's aiming through the focal point. See how I have like a dashed line? Aiming for this focal point. So, and remember, there's really an infinite number of focal points. So, all right, so let's get rid of this one. That's not right. That's for a diverging lens.
How do you know if it's converging or diverging?
You just know by the shape. You just look at it. Yep.
Right, that's what I'm assuming. So would concave just be the exact picture we drew the first time, but the opposite?
A concave lens?
Because
Well-
if it's gonna be a convex lens here,
Uh-huh.
going this way, then it's gonna be a concave near
Yeah, it's not, I think if I understand your question, but it's not quite that simple. But you're on the right track. All right, where did this light come from? Top or the bottom of the object? Top, so that's the top of the image that's formed. And light that goes along the principal axis will do what? Stay on that, so there's the bottom, connect the two, there's our image. Okay? That is a real image. How do I know it's real?
Because the outside of here.
That's outside of the focal point.
It's,
imaginary land.
because there's no imaginary land, that's right. It's made with real light. So it's real, inverted, and the magnification, usually greater than 1. Kind of depends on where you put it because it'll make it larger or smaller. So, now let's look at positives and negatives. 1 over F equals 1 over DI plus 1 over DO. Focal length, positive or negative? Is there real light going through those focal points? Yes. So if it's real, it's positive. The image is real, so the image distance is? Yep, and object distance always positive. Okay?
What's the object is inside the focal point?
Oh, we're going to do that one. So high over ho, negative di over do. This is about right side up and upside down. Height of the object, always positive. Height of the image, negative. These guys are both positive, so does that work? It works. Okay? All right. Now let's do... I'm sorry? Oh, because the image is upside down. All right, now let's do what Peter just suggested and move the object inside the focal point and see what happens. Okay. So it's the same lens, it's a converging lens, so it converges the light to focal points with the object here. Object. Same rule applies, so parallel light will exit through the focal point. That's a converging light ray, so that's all good. And then the other one, this is tricky to draw. So this one was parallel through the focal point. Now we need to go through the focal point and exit parallel. I'm just going to make the right choice for you so that you don't see the wrong one. But I'm going to aim the light through this back focal point, like that, and have it exit parallel. Okay?
I mean? Like, what happens if that line?
Oh, like you
the,
miss the lens,
Yeah.
you just make the lens taller. In Gina's perfect notes, there was chaos. What? Like, if I go home and look at your room, is your closet organized? Oh, my gosh.
Her handwriting is terrible, like, you should see her math, but it's so.
That's right. Okay, so where will these two light rays meet? They will not, so they make a virtual image back here. Oh, look how magnified it is, too. In fact, if I were to put a handle on this lens and walk up to it and go,
Magnifying glass?
hey, look at this object. When I look and I collect this with my eye, it looks bigger. It is a magnifying glass.
Oh, geez, extra credit point?
No.
You tried so hard.
I know, it's kind of a thing now. Okay, whoopsie. I was.
Is that first dot on the bottom of focal point?
First, where?
Farthest to the left.
That?
Yep.
Yep.
Thank you.
So now we're going to attach the positives and negatives to all this stuff. Real or virtual image?
Virtual.
Yep, it's a virtual image. It's upright or erect. And the magnification is definitely greater than 1. Okay. So now let's put positives and negatives. Focal point, positive or negative? Focal length, is there real light going through that? If there's real light going through at least one focal point, it is positive. Go ahead, Gina.
For lenses then, the only time you can have virtual images is when it's behind it?
Yeah. So positive, positive. Image distance, when it's virtual, positive or negative?
Negative.
Yep. This is upright versus upside down. Height of the image, positive or negative? Positive. Height of the object? Positive. Image distance is negative, so then we have negative, negative over positive. Does that all make you happy? Good. That is correct.
I would say this is image was, negative.
Because it's virtual. That's the definition of a negative image distance. All right. I think I have enough time to do the last one. And then tonight's homework, similar to yesterday. Try a problem from 15B, try a problem from 15C. And tomorrow we're just going to practice this, okay? Can I move this yet? This is online too. I'm recording. Okay, last one. Last one is a concave lens, which is diverging, okay? Diverging lens. And, oh, by the way, this lens that makes a real image is the lens that we're using in this projector. It's the lens that they use at movie theaters. Makes a real image. You walk in front of the screen, the image is on your face. It's real. This is also the lens in your eye. Have you ever heard that the images in your retina are upside down and your brain flips it?
Yes.
That's true! We're going to talk about that on Friday.
Are you serious? That's awesome.
Well, not exactly. There's a probably pretty unethical experiment that was done on a bunch of people. So, all right. All right, guys, listen.
So much knowledge.
So this is a diverging lens, which means all the light rays have to spread out. Diverging. So that's the basic rule that we have to follow. Yes. So a parallel light ray will exit through the focal point. Which focal point to be able to diverge? Do I want to go through the focal point on the right or the focal point on the left? You are correct. Divergent. So it's a diverging lens. It spreads the light away from the principal axis.
Okay,
Spread it away.
understood.
And the reason this works is because of the fish example. That's the way the light bends, okay? Now we got to do the opposite of this. So head it through the focal point and exit parallel. We're going to actually use this focal point. So I'm going to aim through this focal point and exit parallel. Is that diverging the light?
Yes.
A little bit, yeah. And where will these two light rays meet? Never. So we will create an image in virtual land. It is demagnified, it is virtual, and it is upright. So virtual, erect, magnification less than 1. And if you think about this, if I'm standing over here and I look through the lens, what do I see? What do I see? This is the object. I see the image. So when I look through a lens, a diverging lens, it makes the object look smaller. Smaller, which gives you the illusion that they're far away. You know how small stuff looks like it's far away? Right? So that's why. It isn't necessarily farther away, it's just your brain thinks it is. This is like looking backwards through binoculars, if you've ever done that.
Does it, like with the glasses, does it have anything to do with the fact that, I know without my glasses, everything seems like really special, like it's just like a light bulb. Just
Okay.
glows, you can, I don't know, you see a blur all the way around it.
Oh, that's because you have an astigmatism. That's a different thing. We'll talk about that. Yeah, we're going to talk about the eye and how it works and nearsightedness and why these lenses correct it and your eyeballs are all too long. But you're all going to eventually have surgery that'll correct it and it'll be done in like 30 seconds. We have it right now, actually. We'll talk about this on Friday.
I do.
All right, so let's do positives and negatives here. Focal length. Does any light go through the focal point? This is a weird one. Light does not go through the focal point, so is that a real or a virtual focal length? Virtual, so that's negative. Object distance is always positive, and image is virtual, so that positive or negative image distance? Negative, right. Magnification is greater than 1, blah, blah, blah. These are both right side up, so are those positive or negative?
Positive.
Yep. And the image distance was